Hello, so in this video I wanna do some examples about prescribing the spring force in different situations. And let us remember the general expression for the spring force. Okay, so let us consider kind of something that's similar to a pendulum, but instead of being suspended by an inextensible spring, we're going to suspend it by an inextensible string. We're going to suspend it by a spring. So this is my origin. This is planar motion. ER is going to point along the position vector. R, and then E theta, well, let me draw EX and EY this way, and then E theta, theta is like this and E theta is like this. Okay, notice that I have EX, EY, and then E theta, ER, and E theta. So ER, E theta is EX, EY, but rotated by an angle theta. So as the pendulum moves, ER and E theta change. Notice that EZ does not change. EZ, which is ER cross E theta, which is EX crossed with EY, does not change. Okay, so if you do the right hand rule, okay, how will I explain this in the video? Well, if you do the right hand rule, if you have your thumb and then you're curling your fingers, if you put your thumb like this and curl your fingers out of the page, your fingers are gonna trace this vector, this arc, omega, and your thumb is gonna point along EZ. We call this EZ the axis of rotation. So what's happening here is that ER and E theta are rotating like in this arc, like in this omega, and the axis of rotation is outside the page, pointing towards us. So it's always the case, and I'll do some examples in another video, that in the cylindrical coordinate system, ER and E theta are gonna rotate in the EX, EY plane, and EZ is gonna be perpendicular to the plane of rotation. So okay, EZ is perpendicular to the plane of rotation. Okay, this was a small tangent. Let me maybe copy this figure again. And paste. And let's copy the general expression for the spring force also. Copy and paste. Okay. So in this case, RA is just 0 because the fixed end of the spring is at the origin, and R is just the position vector from the origin to the mass, which is R, ER, the regular position vector we know from cylindrical polar coordinates. Okay, so if you want to calculate R minus RA, that's gonna be RAR minus 0, which is RAR. So R minus RA over R minus RA is RER over the magnitude of RR, which is the absolute value of R, scalar, but R is positive, so this is just gonna be ER. And so when I write my spring force is gonna be K, the magnitude of R minus RA is R, minus L0, just replacing 1 by 1, minus ER. So this spring force is gonna holds always when the spring is even compressed or stretched, is gonna hold. So it always holds both when spring is stretched or compressed. And for any location of the mass described by this configuration. By this configuration. Okay, so that's an example. So even if the motion seems complicated, we can simply find the expression for the spring force. Let us look at another example. Maybe, let me see, how can I insert image and this image. Okay, very good. No. And I need to add a page, blank page. Okay, very good. Just let us fix this up. Can we delete this page? Whatever. Okay, so the slider of mass M, by the way, I do not want to solve this problem. I only want to prescribe the spring force. But just to read it, the spring of mass M is confined to the horizontal slot as shown. The two springs, each of constant k, are linear. Derive the nonlinear equations of motion for small values of y, returning terms of order y cubed and larger. For both springs are unstretched when y is equal to 0. Okay, so both springs are unstretched when y is equal to 0. What does that mean? Unstretched. So when y is equal to 0, the mass is here, the springs are like this. The length of the spring, L0, is just L. So the initial length, the unstretched length of the spring is L0. Then if I have the mass, and I actually have two spring forces acting on it, but they're gonna be equal because they're symmetric. So kind of equal in magnitude, but they have kind of symmetric directions. Let me try to find out what these directions are. I'm gonna clear up the figure, erase everything on it. Okay, and take, so they give us that EY is like this, increasing along EY, and I'll take EX to be like this. Okay, so let me see. Let me consider one of the springs. It's this spring here. This is spring. I'll take the origin to be at its base. I have EX, EY. This is a top view. And in general, the spring is like this. And the mass is moving on a horizontal line. This distance is L. And this distance is y. So then if I want to write the spring force is minus k r minus ra minus L0 minus r minus ra over r minus ra. because I took my origin to be at the RA is here 0. Okay, and R, what is R? Well, R is LEX plus YEY. So the magnitude R minus RA is LEX plus YEY minus 0, which is just this, LEX plus YEY, and its magnitude, excuse me, and its magnitude is the square root of L squared plus Y squared. So I can write that the spring force is just minus K, the square root of L squared plus Y squared minus L0 over minus LEX plus YEY over L squared plus Y squared. And that's it. That's it for this force. For the other direction, this is for this side. For the other direction, I'm gonna limit Fs1, Fs2. Fs2 is the same because it's entirely symmetric, except that instead of pointing along minus EX, it's gonna point along EX. So this is Fs1, Fs2, minus LEX plus YEY over L squared plus Y squared. Okay, so the point of this video was just to show you that no matter what the setup is, you can apply this equation, simply find R and RA and substitute, and you should be able to find the expression of the spring force simply, and it applies always. You don't have to worry about the signs, whether the spring is extended and compressed or so on. And here we just, one more thing I want to do is replace this L0 by L, because we know that L0 is L from kind of our initial calculation here. Okay.